Alright, hell yeah, we got material mechanics, and what we're going to do is an elastoplastic problem. And some of them are just cool because they're easy. Because all we're saying is like, hey, each of these bars is going to be at their absolute max. And so the equation that we're going to be using is stress is force over area. I like to think this is like maybe like braking strength, braking force. And basically we're going to say, hey, this is the yield stress and yield force divided by area. These are the two you put little subscripts on. The area is already predetermined, and it's already given. Cross-sectional area is 0.307 inches squared. So we can rearrange for this force yield, and we get, and the yield is going to be 36,000 pounds per inch squared times 0.307 inches squared. 0.307 inches squared. So let's do that. Alright, so hell yeah. So we get a force of yield of 11,052 pounds. So that's each of these members. It doesn't matter what angle they're at, because we're just going to take them all to their yield and figure out what force that is. Or, I mean, once all of these are at their max, each one of them is going to be at 11,000. It doesn't matter which one happens first. But we might as well learn something, so we're going to take a step back and learn something. So let's say all of these tubes are 1, 2, 3, 4 are just in a line, and we're gonna throw a force on them of P. You know what I mean? So want all of them. So there's two different things, because the other equation is strain is change in length over length. These are two different things. Same thing. You can have a braking strain. That's going to be your change in length that causes it to go plastic. Or your yield strain is the change in length that causes it to yield times length. So we could change this length, and they're all going to change length at the same time. So they're all going to reach, from geometry, they're all going to reach that yield stress at the same time. So now we need to figure out, it's like, even just looking at this, which one's going to get yielded first? We might not know, and so we have to, since we have an angled problem, take it to the extreme. We already took it to one extreme, so now we're just going to say like maybe two bars that are totally straight across. And what happens if I bring these bars down like 1 inch, let's say? Well, this bar, and let's do a 2D drawing. So we're going to go there to there, and we're going to come down to here. Well, look at this. This bar did not change length by very much. Like probably this bar changed in length that much. So now I think you get it, because now we're going to I guess do this scenario where we have two bars that are identical, and then we're going to change their length. We're going to pull them down by 1 inch. So vertically we're going to pull down 1 inch here. Vertically we're going to pull down 1 inch here. Well, guess what? Each of these bars lengthen by 1 inch. So, and maybe you'd want to do one in between, but what it's saying is that the bars that are more vertical, this bar B and C, are going to lengthen first. The bars that are out to the side, so let's say we have bars like way out here, by the time you pull down and lengthen BC, the bars that were way out here didn't lengthen worth a damn. And so there you go. And yeah, this problem could be more complex if you were analyzing it, because hey, this bar is longer. You know what I mean? So there might be a little ratio in here, because sure, when I pull down to here, yeah, these bars lengthened. No, this is good to analyze. These bars lengthened more, but they're shorter. So basically, strain max is change in length max divided by length, and so we're saying that. These bars are shorter than these bars. So these bars won't lengthen as much anyway, and they're longer. You know what I mean? So there you go. So I think that kind of proves it, that obviously these two bars will go plastic way later than these two bars. But now let's get back to why this problem is simple, because we're taking all the bars to this 11,000, and it turns into just a very basic statics problem. Alright, heck yeah. So I say very basic statics problem because we already know the forces on all those. So, and I'm just going to do it like this. I'm just going to use this drawing. So we have P down here, and then we have force D, do an arrow, force C, do an arrow, force B, do an arrow, force A. Well, guess what? A equals B equals C equals D, because they're all at 11,052 pounds. So now we can use our sum of the forces in the y direction, and that's the only one. These are so balanced that we just do sum of the forces in the y. And now check this out, because we're going to do it kind of in a cool way. And we'll take maybe these forces up to here. Maybe that's what we should have done, because visually it'll be cool and it'll make sense. I guess you don't have to do that, but one way you can... what we need to know is the vertical components of each of these forces. So, there you go. The vertical component is basically, you know, to there. So if we said, well, like, I think these are like at 45 degree angles. So yeah, the vertical component is going to be like 0.707, because if I knew this angle was 45, I do like, one of my subscribers, probably not a subscriber, doesn't like the sun is shining, but I swear to God, it's like, I don't make these little shortcuts, you know, I mean, I think they're useful for me. I still use them. I mean, actually, I came up with this one, but it just makes sense. This is the sine component, but I want the vertical component, so that's the cosine. So I'm going to say that if I know this angle, theta, cosine theta, or the hypotenuse times cosine theta, so 11,052 times cosine of 45, that's going to be 11,052 times 0.707. So that's going to, so cosine 45 is 0.707 times 11,052, and I get 7,815. So that's the component of this one. But I don't want to do it that way. I'm going to show you a different way. So some of the forces are 0. I'm going to say, hey, I know this force is 11,052, and now... but the other aspect of using sines and cosines, it's like, yeah, this is the hypotenuse. It's the bigger number. I want to know the vertical component. That's always going to be a smaller number. So I'm going to take the bigger number, the hypotenuse, and then I'm going to multiply it by a fraction. This is going to be something between 0 to 1. You know what I mean? That's essentially what we're doing here. And because we have a length component, I can be like, hey, this is 36, and then I can know what this hypotenuse is. So I can do a ratio of 36 divided by, and then this hypotenuse is 30. This a squared plus b squared, square root that. So I'm going to go square root of 36 squared plus, what the hell is this? This is half of 54 divided by 2. So that's 27 squared. Cool, and that's that. That if I did this calculation, that would be a percentage, and let's do it. 36 divided by the square root, 36 squared plus 27 squared, and that's 0.8. Cool. Yeah. So we have it's a 3, 4, 5 triangle. You know what I mean? If this is 0.8, this is 0.6. 0.8. Cool. Anyway, and then there's 2 of those, so we can just, you know, don't have to do too much writing. So it's that one and then that one. Those 2 vertical components. Now we'll do these ones. So we're going to do that same 11,052 pounds, and we're going to multiply it by, so this is 36. That's the vertical component in height, but now the square root of 36 squared plus whatever this is. This is 54 divided by 2, so that's that length plus 21. Cool. Oh, that's 48. So this isn't a 45 degree angle. So we got 48 squared. Cool. And now we're going to go 36 divided by the square root, 36 squared plus 48 squared. And that's 0.6. So this is 0.6, and now this is probably 0.8. So we have like a 3, 4, 5 triangle just in the opposite direction. So cool. So we got 0.6 here and 0.8 here. And then we got two of those, and those are going to be equal to P. Because you could be like positive these forces minus P is equal to 0. That sum of the forces is equal to 0. Might as well get P on the other side, so it's just equal to P. So cool. So I'm going to do 0.8 times 11,052 plus 0.6 times 11,052. And we get a P is equal to 15,473 pounds. And hell yeah, did we do one pretty fast? You know what I mean? Just about 10 minutes, stuff like that. So we have 2, 12, 5, 2, 12, 5. Now we probably hella messed it up. 47.9 kips. Oh, holy Toledo. No, all the bars are not symmetric. They didn't draw the picture very good. So each of the two inner bars has an area of 0.6. So ours was right for what the hell we were doing. But if the inner two bars have an area of that, we're going to take this 36,000 times 0.601, and we get 21,000. See, I don't read the problems. And I think that is the problem. Anyway, so we get 21,000. That's the inner bars. That's going to be this 0.8. So we're going to have that times 0.8 plus 0.6 times 11,052. And holy hell, we're still like way off. All right, that's what we love about, I've said I want errors because we want to be able to figure out how to solve them quickly. So our yield force is 36,000 times the area. I get it. I get it. We didn't multiply by 2. I don't even think we ever multiplied by 2. For the love, you know what I mean? So yeah, we would have whatever this number was multiplied by 2. We would have got pretty close, but we still would have been off. Alright, so we got, oh, no. This was our new number for the inner bars. So, outer bars, inner bars. Alright, now we're on a roll. Inner bars are right here. So we got 2 times 21. Oh, and we're losing light. Man, this is a train wreck. Alright, we got 2 minutes to crush it out. So we have 2 times this 2,663. Times 0.8 plus 2 times 11,052 times 0.6, and we get 4,700 oh my god, 47,880 pounds. And if you do 3 significance figures, this is 47,900 pounds. And then bring it in 3, and you get 47.9 kips. And I finally found out that it is just K. K is kips. You don't have to write out kips. Holy Toledo. Alright, we did good on that one. Not really, but we did it fairly fast. And again, you're just taking all the bars to their max. I just didn't read the problem that the two inner bars were different. So obviously. And then I got into trouble, and I didn't multiply by 2. Anytime you do this type of stuff, just do triple star, and then do some triple stars over here, so you can make sure you don't make those mistakes. Yeah, making mistakes of a factor of 2, it's very common, and that's how people die. Alright, thanks for joining me, and that's a video.